Let's dive into the fascinating world of hurricanes and the complex atmospheric conditions they require to form. Hurricanes, or tropical cyclones, are colossal storms that thrive on specific ingredients. First, they need a warm ocean, like a giant heated pool, with temperatures of at least 26.5 degrees Celsius. This warmth acts as fuel, causing evaporation, which adds moisture to the air. As this moist air rises and cools, it releases heat, energizing the storm. Imagine it as a pot of boiling water. The steam rises, carrying energy with it. Next, the wind shear must be low. Wind shear is the change in wind speed and direction with altitude. If it's too high, it can tear apart the storm before it even gets started. Finally, there must be a pre-existing weather disturbance, like a tropical wave, to spark the storm's rotation and formation. Now, let's talk about the Coriolis effect, a crucial player in hurricane formation. This effect is a result of Earth's rotation, causing moving air to be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. It's like spinning a basketball on your finger. The spin helps to keep it balanced. For hurricanes, this deflection is what enables the cyclonic rotation they need to form. But here's the catch. They can't form near the equator, because the Coriolis effect is too weak there, so they typically form at least 5 degrees latitude away. Picture the Earth spinning on its axis and how it affects everything from ocean currents to weather patterns. Hurricanes evolve through several stages, beginning as a tropical disturbance, a cluster of thunderstorms with minimal organization. With favorable conditions, they can develop into a tropical depression, which is characterized by a closed circulation and winds up to 38 miles per hour. If the storm strengthens further, it becomes a tropical storm, earning a name and exhibiting more organized structure with winds between 39 to 73 miles per hour. Finally, when the winds hit 74 miles per hour, we have a hurricane. These stages mark the storm's progression in both intensity and structure, ultimately leading to the well-defined eye and eye wall of a mature hurricane. Not all disturbances become hurricanes. Several factors can limit their development. Dry air intrusion can halt a hurricane's growth by promoting evaporation, which cools the storm and disrupts its warm core. Land interaction is another barrier. When hurricanes move over land, they lose their primary energy source, the warm ocean water, and their structure is disrupted. Additionally, changes in oceanic and atmospheric conditions, such as cooler sea surface temperatures or increased wind shear, can weaken the storm structure. Understanding these limiting factors is crucial for predicting which disturbances will develop into powerful hurricanes. The Saffir-Simpson hurricane wind scale is used to categorize hurricanes based on their wind speeds. Developed in the 1970s, this scale ranges from Category 1, with winds of 74 to 95 miles per hour causing minimal damage, to Category 5, with winds over 157 miles per hour causing catastrophic damage. However, the scale doesn't account for other hazards like storm surge and flooding, which can be just as devastating. Recent discussions have considered the possibility of adding a new category to account for increasingly intense storms, a reflection of the growing impact of climate change on hurricane intensity. The historical impact of hurricanes on U.S. coastlines reveals significant trends. Over the decades, the frequency and intensity of hurricanes have varied, with an increase in the likelihood of major storms. Economic impacts have escalated, with costs rising dramatically due to both storm intensity and increased coastal development. Socioeconomic effects on communities have been profound, with many facing long-term recovery challenges. These trends underscore the need for effective adaptation strategies, such as enhancing building codes and investing in resilient infrastructure to better withstand future hurricanes. Finally, let's explore how advancements in forecasting technologies are enhancing our ability to predict and respond to hurricanes. From high-resolution satellite data to the integration of AI, technology is playing a crucial role in improving forecast accuracy. Uncrewed systems like drones collect critical data, while reduced atmospheric friction in models has led to better intensity forecasts. These innovations, along with collaborative research efforts, are paving the way for more accurate predictions and better preparedness strategies, ultimately helping to safeguard communities against the devastating impacts of hurricanes.